text. This is a seminar about gender and technology. My focus will not be on gender specifically, but more on what bias is and when is bias unfair. I have provided examples with gender, but I could just give a version of the presentation with ethnic background or socioeconomic background. So I'm focusing on those subset of gender problems, which are basically the same problems. And it's really more conceptual about what is bias, what makes an algorithm fair. And as you may imagine, also in the context of the project in collaboration with Christoph Heitz, who is professor of data science at SAVE, in the past, I've been working a lot also on the mathematical side with the computer scientists. And where we started from was this idea of the statistical fairness metrics. The simplest you can have are basic observational group fairness metrics. We're basically comparing groups with each other. These are also the ones that are standardly used in journalistic coverage. And here I put a picture, which I guess some of you may have already seen one time or another, if you are in the tech fairness or tech ethics space, because this journalistic investigation really made the debate explode. Research into non-discriminatory algorithms had been flourishing for a decade at least. Actually, I found, I may have my biases, but in my research, I found that the pioneering papers were actually born in Europe, Italy, PISA, the PISA group specifically, and in the Netherlands, which is unsurprisingly given how innovative they were in embedding philosophy in polytechnic studies. So unsurprisingly for the Netherlands, perhaps most surprisingly for Italy, there had been several rounds of European projects working at the intersection between the law and non-discrimination law. And at that time, the debate was driven by privacy experts who were trying to conceptualize non-discriminatory algorithms in a way that were quite similar. Then we had similar approaches in the US with centered work, individual fairness. But group fairness metrics still remain very prevalent in those approaches. And when this article by ProPublica came about, that discussion really exploded. So this article was about the fact that false negative and false positive rates were different by racialized or race groups, as the American people more easily say, in a way that was argued was beneficial. So both of them, both the false negative and the false positive, was beneficial to one group in particular, the whites, because basically the false positive rate. So if you were an innocent or a person later not to reoffend in a prediction of whether you would engage with the same crime after being released from prison. So if you were a person later to reoffend, you were more likely. If you were later to reoffend, you were less likely to be identified as such in case you were white, and which seems an advantage, right? I mean, you are predicted as someone who will not be a reoffending person, even if you will be reoffending. And if you are non-reoffending person, so someone later not to reoffend, someone who will behave well, you were actually more likely to be identified as someone who will reoffend, so someone who should be kept in prison, basically, if you were Black. So it seems that both on both counts, on the false positive and the false negative, both were advantaging one group. So this is quite different from the standard situation where we have a ROC curve and we have some trade-off between sensitivity and specificity. And then the bubble sort of exploded because there were so many viewpoints. The company reacted to this by saying, look, our algorithm is a good algorithm because it's group calibrated, the same probability of being correctly identified. And then there were papers rediscovering what actually had been known in statistics for decades, namely that when you use the, you can satisfy all of them, which require for some sort of parity, moral goal to be achieved, which of course is intuitive because anti-discrimination has something to do with receiving the same treatment in similar circumstances. Basically, the group metrics interpret differently what it means for people to be similar or in similar circumstances. And some group metrics are looking at the future, like what in informatics would be the true label value. Some of them are looking at the risk. It all becomes really confusing really fast. What I will do today is actually to go beyond this approach, which is a way to show its incompleteness. And some of you who are really into the debate, enthusiasm, the computer scientists, hey, we are clever people. I was about to say guys, reflecting a gender bias. We're clever people. We can fix social if you're a certain gender. We are totally now in the opposite phase, in which you problems which are social all the way down, which means that mathematization, or at least the blind. So where is the novelty in this talk? That I'm basically not pursuing a sociological line, but I'm going to look for one distinction between biases that has been overlooked. It has been overlooked, at least in the computer science debate. It has not been overlooked in a completely different context, the context of criminal trials. That's where it comes from. I'm going to ask you to accompany me in this mental exploration, and let's see what our moral intuitions tell us. So we're really working here with the ground material of our ethical intuitions. No maths, more intuition and ethics. Okay. So imagine a situation like this, that we have two algorithms age, income. Sorry. To unmute. Before, the outcome. How are these different, and why are these morally different? And are they actually different? Now, I think this is quite a plausible hypothesis, and as a matter of fact, in our paper we defend it. Now I want to go a bit beyond this and again do this trip with you and see what your reaction is, if you think this can explain it. So here is a scenario which creates some tension. So suppose that research shows that people who have committed violent crimes develop distinct speech patterns during interrogation. So these patterns emerge after committing the crime and due to having committed the crime. Let's assume there is a plausible causal mechanism there. But it so happens that the pattern occurs more frequently in certain genders due to psychological differences. And an algorithm is developed to detect these patterns in interrogation recordings. So this evidence is diagnostic in the causal sense, yet probably we are not so easy to use it. And again, this is a bit of a question. One can find multiple explanations while this doesn't seem fair. Maybe it has nothing to do with fairness, but it's more, we find it appalling, this sort of, I just call the truth machines. But maybe it's really that the causal framework does not fully explain what's going on here. And further evidence that it's not just causality playing a role can be done by looking at another case. But before I introduce this last case, let me introduce a different conceptual framework. So far we've said, well, there is this diagnostic predictive distinction, and we can model it in terms of causality. But we could also model it in terms that are epistemological. So we could say that evidence is diagnostic if it focuses on information that becomes relevant after we know about the fact. So an epistemological distinction wouldn't look at the causal model of the world and ask, is the evidence causally downstream or upstream? But it will look at the causal model of the world and ask a different question. It would ask, is this causal model of the world something that I have produced after knowing about the context and based on what I know about the context? Or is this a fully general causal model of the situation of the world that doesn't have any information from the peculiar case? And this offers an alternative interpretation of what makes a detection a form of prediction or diagnostic decision different in the two cases, in the predictive and in diagnostic case. So the diagnostic evidence will be evidence that the relevance of which can only be understood after specific case details are known. So we build our causal model of the world from a posteriori evidence. Well, the predictive evidence is evidence that can be applied based on pre-established statistical patterns. And actually, this distinction is fully orthogonal to the other one. So we can have all four combinations. So now we can test whether the causal distinction is relevant by considering a case of something which is predictive from the causal point of view, at least on one reading of it. In the paper, we try to achieve a synthesis of these two things, but I think it's simpler to see in this way. So something that is causally, from the causal point of view, looks like predictive, But from the epistemological point of view, it's not. So consider this. So first we go for the fully diagnostic case. Breaking and entering. Footprints found near a broken window were caused by the act of breaking in. The perpetrator had to touch the floor near the window to break it. And these footprints are causally downstream from the crime. Had the perpetrator not broken the window, well, the fact we're trying to predict is breaking in. That's the crime, not anything else. So if you want to visualize this, really imagine that the footprints are found after the window. It's jumping from a window and it's a floor immediately after the window. So this feels like legitimate evidence, and it's diagnostic both from the causal point of view and for the point of view of our knowledge from the epistemological point of view, because in order to say that this footprint is relevant to, for instance, acquitting or convicting someone accused of a crime, we need to know something about the crime. We don't say, well, people which this size of shoes are inherently more likely to commit crimes, which is more the sort of statistical approach when you use Bayesian reasoning and you take into consideration base rates, for instance. This is a very specific footprint, and the relevance of that footprint for the probability of this person having committed a crime, it's fully dependent on the specifics of the case. It's not a general pattern in the world. There may be no general pattern, no correlation between foot sizes but maybe there is a correlation between foot sizes and gender. So even using these creates some sort of gender bias. But I think we will say, well, that's not a sort of gender bias that interests us, no matter what the matrix says. It's diagnostic. Well, I think we can also have similar intuitions if we consider a case which is diagnostic from the epistemological point of view, but at least not so clearly diagnostic from the causal point of view. So consider this case, murder in an apartment. Footprints are found near a doorknob in the victim's apartments, and they were left when the person visited earlier in the day, before the murder. So this cannot be causally downstream, because nothing can cause an event so the event, the crime, what we're trying to predict, cannot be the cause of the footprint because the event happened later, right? So the evidence comes from before. So what is our intuition about this evidence? It's predictive from the causal point of view, at least if we interpret predictive in terms of certainly it's not diagnostic. Certainly it's not caused by what we're trying to predict, the murder. What is it? Well, if we look at it from the epistemological point of view, so if we adapt the second framework, this is diagnostic. And what makes it diagnostic is not the position in the causal graph, but it's the fact that we are relying on a graph, on a causal model of the world, which we only have if we have investigated a murder. So it shares with the previous case this epistemological property. But it's not based on some sort of general pattern of the world. Again, we're not saying people who have a size 36 are more likely to murder people. We're saying, no, for this specific crime, people, the person who committed the crime most likely has a size 36 because we found evidence. Of course, it's diffeasible like every statistics, but it plays a different role, and it plays a different role. And I think the bias that it creates, because clearly foot sizes are related to gender via sex, we could say, if at least some genders are statistically correlated with sex. If this happens, then I think we have a bit less objection. Yeah.
So how we decided what is the optimum weight we are giving to something like size of the foot or the fingerprint in the hand? Because the weight we are giving in the algorithm that decides the biasness, and that brings the biasness in the whole algorithm, the output. Like I'm asking, like there are different parameters when we design an algorithm for with respect to some input, it is giving some output. Then there are different parameters, and to each parameter we give different weightage.
I don't even know whether I don't know how to make diagnostic. I'm an algorithm, let's say, based on diagnostic evidence. So suppose that algorithms necessarily work on evidence that is predictive in the epistemological sense. So even when it's after what we need to find out from the point of view of causality, it's always general. Maybe we end up discovering that this is the case because at least if we develop algorithm through machine learning, we need lots of instances. So how can we train algorithms about specifics, right? So if this is what you're asking, one possible answer is that probably we have a problem with algorithms. But the problem is not captured by the metrics, because we can imagine the legal system and we can imagine applying metrics. We can imagine thinking human beings and saying how likely are them to make mistakes. And well, they're likely to have a bias here in some sense if you aggregate these decisions in a world in which you can use footprints to make decisions. You can create some gender bias compared to a world in which you only use features that have no correlation with gender, if any such exist. But intellectually, we can arrive at it, right? So you start with a world that only uses to make decisions features are not correlated with gender. And then you have a world in which you can use footprints. Footprints introduce bias, even if you're not using algorithms, even in a human process. I think that's something we can quite confidently say because they're correlated. Now, the point is that I think in this case, even if some sort of gender bias is created in the process, in this familiar process of assessing evidence that's connected to specific cases, we don't feel that this bias is such a big problem. At least we don't feel it's such a big problem like in those predictive algorithms, where we are trying to make inferences about general patterns. So also look at the difference with the speech patterns, which relies on general theories about how criminals speak. That's the enemy, if you want to say. That's the fellow. I'm saying that's something apart from what we can measure in terms of likelihood of receiving a conviction, for instance. That's something deeper, it seems to me, about those algorithms that are based on information which is not related to the case. And this is what always happens when we use, for instance, Bayes rates, right? We're saying, okay, people from these specific demographics have so much higher probability of committing a crime. No idea why. It may just be a correlation. Nobody's saying it's causation, but in ordinary Bayesian reasoning, if you have a base rate, you use it. You use it. You modify your final assessment, probabilistic assessment based on that. But here we're saying that something really peculiarly unfair, or at least more problematic from the point of view of fairness, in this sort of like super generic statistics and how they influence the decision, which is not the case when we are dealing with errors which are due to evidence which is more contextual, like the footprint case. Both of them, both the one in which, causally speaking, the evidence is produced by what you're trying to assess, the crime, and both when it comes before the murderer or alleged murderer visiting the apartment before the murder. So here are my key insights. Case-specific relevance often matters more than causal direction, probably. Evidence that connects individual to specific circumstances and not just broad categories seems to be less problematic for bias and fairness, even when, statistically speaking, it introduces some statistical disparity. And on the contrary, and this is in favor not just of the general diagnostic predictive distinction, but of the epistemological interpretation, even evidence that is diagnostic in the causal sense, evidence that's produced by what we are trying to detect, seems problematic when it's not connected to specifics, or it seems more problematic than evidence that's connected to the specifics of a case. So the algorithm for crime scene analysis, if you want to call it algorithm, but algorithm doesn't have to be, machine learning stuff. Algorithm can be a procedure to do things that people are required to follow step by step, that identifies whose footprints these are, because you find footprints on the crime scene, and then irrespective of when these have been left, and even if it clearly causes some sort of bias, because you will not, it will count as evidence against people with a small foot if it's a small footprint. It's not impossible someone with a big foot does it, maybe has bought a very special type of shoes. It's much less probable. So it's still a case of probabilistic reasoning, but it strikes us, I think, as less problematic. And this level of analysis isn't captured by the standard fairness metrics, and also the less standard ones, I would say. I mean, it is not just limited to group fairness metrics. And well, here I'm just mentioning the most famous group fairness metrics, but I think this extends to individual fairness and more sophisticated constructs. And then the key question is, if we take this seriously, that's a different question we should ask, or at least an additional question we should ask when assessing the algorithms for gender bias, which is not just what are the statistics saying, but also, are we using an algorithm connecting individuals to outcome, taking into consideration specific circumstances, or purely through statistical generalization? And maybe this makes a moral difference. So this was my key message. Again, this is quite exploratory, and I owe a lot of the ideas from years of conversations with Marcello Di Bello and Niccolò Cangiotti across the ocean, and also some further references of places where you can find this debate, which are quite outside of the literature that people, even IA ethics, usually draw from. So I hope it was not too crazy and difficult to follow. Thank you very much for your patience.
Like I feel while we design the algorithm and while we train the machines, so biasness that come into the whole algorithm or the decision-making system comes from either the lack of the data or the or you can say the diversity in the data we have. And the other thing, the other use case where we can have the biases is because of the lackness of the comprehensive understanding of the expert who are putting the weight or giving the weight to each parameter. Suppose there are some different like weight, fingerprint, footprint, and all that. So they give different weightage to different things. And that's how they give some less weightage or more weightage to something which is not appropriate because of their understanding. Sometimes it is because of the expert who are designing the algorithm, and sometimes it is because of the lack of the data, and sometimes it is because of the limitations of the algorithm or some method which we are using to evaluate the whole output. Just curious, like how we optimize this whole thing in so that we can have minimum biases in something which we decide.
So first of all, I think we need to, thank you for the question. We need to distinguish between a sort of a hand-coded algorithm where you ask experts to put weights from a machine learning algorithm, where basically you let the data influence what the weights are, and these are the weights are eventually decided by some mathematical technique, backpropagation, for instance, if you're using neural networks. Gradient descent, so these sorts of things. That's not about experts transmitting their bias by deciding weights based on their domain knowledge. And I think your question suggests, for the second case, the data-driven case, that if only we had comprehensive data, then we will not have the problem of bias, right? Two problems with this proposal. First of all, I don't think we have a rigorous definition of what comprehensive data means. Second, even when we have comprehensive data, if you are dealing with a skewed distribution, you're gonna be back to the compass problem. So let's assume that the compass problem is like a nest of different types of wires, all sewed, all nested one into the other with the feedback loops. It's a total mess. So I assume most likely there are perceptual biases, psychological biases, influence of racism, even in the discovery process. So the data is biased in multiple ways. But that's also a matter about populations, or different rates of crimes exist in different areas, for instance, and can be statistically associated with different ethnicities or races, as they call it in the US. But let's assume a simpler case, a case in which quite simply, do you have more predominant rates of something? If you don't want to think about crime, think about cancer in one group than in another. Like a cancer that is more common in men than it is in women. We can find a lot of these cases in medicine. If you're dealing in a case like that, even if you have all the data, and you have as much data about men and women, there is no selection bias in your observation, no measurement bias, nothing of that sort, you end up still in a sort of dilemma where you have to choose whether you want to have, for instance, a predictor which always says the same thing. So when you say you are a person at high risk, so I predict you as a positive, you have the same probability of being positive whether you are a man or a woman. Or, because if you do this, mathematically speaking, you will have more false negatives in a group where the cancer is less common. So if you equalize for the if you equalize the value of your prediction, then you will tend to make more errors in one direction, in one group and the other. It's quite intuitive if you think about it. It's if it's if your prediction has the same value, so you want to be equally correct, then you end up saying losing, say, more. You're going to have less sensitivity in the group where the cancer is harder to find. So if you want to find that cancer, you should lower your threshold for calling something a future positive, right? Because it's so rare. So there is an influence of the base rate, and vice versa in the other case. So there is no solution to, and there is no conceptual agreement. So some people will still say that you have a bias there. They will still say that if sensitivity and specificity differ for the two groups, you have a bias. At this point, it really becomes a philosophical and a normative question, because you can't answer to someone who claims there is a bias by saying, no, that's not bias, you don't understand what bias is, because there is nobody who decides how to use the word bias in this world. Then we have to, really the only question that it makes sense to ask is, when do we care about those biases and why? We cannot live in a bias-free world. I mean, this very famous theorem has only two exceptions. One, when you have perfect prediction, and the other one is when the distribution is the same for the populations. But that's not the world we live in. We don't world in a world in which we predict or our even diagnostic systems are completely error-free. We don't live in a world in which every group is exactly like every other group relative to the distribution of any variable that we may be interested in.
So the image what you saw like in the first slide, the 2%.
Yeah.
So what kind of biases do you think that were there in the initial design? Like
my point about that case is that the compass case, it's a weird combination of lots of biases from police investigation to, I'm not an expert on US society to tell you what's exactly that, but I can tell you that as long as you have different rates of recidivism in the two groups, then you will face a hard choice between equalizing the false positive rate, for instance, or false negative rate, which will require you to use thresholds of risk in quite a weird way, with some randomization even, and a choice of calibrating the prediction, but then accepting that you will make the sort of errors that disadvantage one group.
So how to suggest that if the data that we got from the police department, and the police department already have the biases,
no, even if it doesn't,
cases, and then how you rectify that?
But what I'm saying is that some bias can be rectified, ideally, like observation bias, all the biases that's related to the instrument or your conceptual lens, we can imagine this to be fixed, ideally. But if you have something that some people call bias, but I think it's a misuse of this term, if you have inequality in society, or even unjust inequality in society. So if you have, for instance, that income is, as a matter of fact, lower in one gender group, then getting your observation rights, getting your lens right, will not ensure that you end up bias-free. Because unless you can perfectly predict income, unless you can perfectly predict the loans, it will always be easier to predict someone who is able to repay a loan with high income, and it will always be easier to predict that someone will repay a loan, statistically speaking, on the male population, because there are more such people. And the only way to fix that bias is to arrive at a society in which income is exactly equally distributed. But then you realize this is not about fixing bias, this becomes about fixing society, if you want. And it's a completely different problem.
But in this, like I attended some similar event, which was made for women, like to bring the gender diversity and all that. So they were also telling this that these algorithms are such that they will tell you that there is a bias, gender bias in your organization and like that. But in that case, I also put this question that might be possible that this algorithm was designed by more of a particular one gender type, not then like while designing that algorithm, how to ensure that this is that algorithm was designed by some kind of mindset which is having one gender biases. Then how?
It's clearly possible if you are hand coding an algorithm that you've got you try to reproduce a model of reality in mathematical formulas, and then you put all of your frame of minds inside. And if your mind frame is biased, then you can transfer it. But which is a good reason, for instance, for having, as they're called, inclusive teams and gender balanced teams. But I think we're also dealing with a different type of problems when you're dealing with machine learning, because the machine learning techniques are men and women who have been trained in computer science, at least in a sort of computer science doesn't consider these problems in depth, will probably be similar, and it will lead to the same problems. Now, if it will make a difference, it's probably because people have been told about the problems that you can have from the data, and then probably the members of the group that is more at risk of suffering from those biases have more motivation to employ techniques to check for these statistics and so on. But insofar as they are sticking to standard machine learning routines, it's not like they're setting weights and parameters by hand. Of course, the reaction can be different. Maybe if you have a team of males with chauvinist beliefs, then they run a machine learning algorithm and they say it's selecting only men for a job. They go, yeah, of course we know men are better. This is only confirming our view. And if you get women in the team, they go like, let's have a look at the data and let's have a look at the stats and what's happening really. But insofar as they are just implementing standard approaches, that's not where the difference lies. Then, yeah.
Sorry, I didn't.
No, but I answered too long and we have monopolized a little bit.
Yeah, thank you for this presentation. I thought it was really interesting what you discussed just now, that perhaps it's not about fixing the data, but fixing society. And I thought it was interesting how you linked in your presentation bias and responsibility in some quite interesting ways through the smoking gun tale story, kind of this murder, and identifying who is guilty and who is to blame. And I'm curious about the role of responsibility or allocating or identifying responsibility in your work.
Yeah, fantastic. Because we built our research on this from previous literature that has kind of thrown a bit of skepticism on the hypothesis of responsibility. So I haven't presented it, but I also added intuition, so one can say, think there's a plausible story to be told that prediction, this sort of predictive evidence is trying to say something about the person that the person has no control. So, if merely being a man or a black makes you more likely to commit a crime purely statistically, and this information gets included in a statistical assessment, there's nothing you can do about it. Not only that, but also this evidence, it's completely indifferent to what you do. I mean, irrespective whether you have done the crime or not, that evidence counts against you all the same. You can't control what other men do, and you cannot build up the statistics on your own. By contrast, this evidence that follows counterfactually from you having made the crime is evidence that only exists because you acted in a certain way. So one plausible path says, well, actually, it's not so much about fairness, but it's about autonomy. That's the value that the world in which we are stepping in, that's all based on statistics and learning from data. That's what it's destroying. So who cares actually about whether how likely is it to be correct? The real issue is that they're destroying the grounds from human autonomy by making basically what happens to you be decided based not on what you do, but what a group that you have no control about does in general or has done in the past. So yeah, this argument has been in the literature for quite a few decades. There are some problems with it because, for instance, one thing Michele wrote in an important essay, important article published in Ethics, is that the issue, at least for instance, in the juridical case, when assessing crimes, is never to consider a person only based on the statistical elements. And we can also imagine in most application contexts of algorithms, you always have a mixture, right? You don't hire the person to work under you or near you for years purely because the computer told you so. So it's always this mix of elements that are related to human autonomy and elements that aren't. And then the case for that the problem is human autonomy becomes less plausible when you take that into account, because it's a much stronger claim. The claim would be that you are disrespecting individuals, you're not treating individuals as agents, as long as there is one or even a few elements that are not agency related. This is less possible.
There is an online question.
Yeah.
If,
Yeah. Can you hear me, Michele?
Yes, perfectly.
Ah, great. So thanks for the call, and unfortunately I missed a larger part of it due to some technical problems, and I might not have gotten the point, but I'm still trying to get your very fascinating introduction of this epistemic approach. And my question is, if I interpret this, making prediction as the trying to say something about about something that I do not know. For example, if a specific person has committed this crime or not, right? So, the only thing that I have is some kind of evidence or data. So, if I say now I have those general correlation stuff, for example, let's say footprint related to gender. This is, let's say, something that I might know or utilize. But then if I detect all those footsteps and I detect them, let's say in specific circumstances, what makes the principle difference to just collecting more data that is more speaking, or let's say more relevant for an individual case? If I would argue, well, it's just additional data that gives me a better way of sharpening my prediction. But where's the principal difference that you think are pointing to?
I mean, wow, because you really went kind of deep, and even without listening to half of it, maybe. No, this is a really penetrating question. So there are different ways that we can imagine making predictions fine-grained. One is to have a model of reality that has little data and then going towards big data. And we have a lot of this in medicine, where the idea is that personalized medicine, what they call personalized medicine there, it's actually not really personal, but it's just taking lots of features into account. And so lots of features that can have different values for the individual case. But I think this is not the same as what happens in the classical investigation case when we feel that bias is less of a problem. Because all of these data, all of these hyper multifactorial model may have been built based on lots of different statistics. And in the case of the investigation, we have knowledge and we are adopting a causal model of reality that only emerges after a specific fact. So it's not just having more information, but it's having access to information which is not available before something happens. Which means that diagnostic information in this sense is quite limited. And there is a range of algorithmic tasks where you cannot use diagnostic one. Like, for instance, if you are dealing with predicting facts that of which you don't even suppose you have one instance yet, really, you are in a case of prediction the future. It may be impossible to have information that is diagnostic in that sense. But it's not merely about adding more and more features to the input vector.
I can understand it, but if I would argue, you know, the fact that it is causally related just gives a stronger Bayesian weight in a sense, right? It's not. You could achieve a stronger let's say a sharpening of your prediction also by other, let's say, collection of classical predictive things. But in that case, you have something that is so sharp exactly by being causal.
Yeah,
you know, that it makes a difference.
Possible. It was. So there are two possible philosophical conclusions here, and we are investigating the second in a paper that I'm probably writing in just 3 months after the first. Because the first hypothesis is to say it's a categorical difference. The different species of information creates the moral gap. But the other hypothesis says it's just that, as a matter of fact, when we move from the probability that a man makes a crime is higher to the probability that this specific man has made this specific crime, the weight of the first probability on the second is actually pretty small. So if when you do the diagnostic one, you're already like into probabilities are much bigger. And so we can have not a categorical, but more of a quantitative argument. The practical lesson is similar, is to say, pay attention, because when you try to make predictions based on those very general facts, and then you need to combine it with other knowledge that you have, either your personal knowledge, or if you are in a committee evaluating some product, or judges. It's very hard to balance these two types of evidence because the evidential weight can be orders of magnitude different. And that's hard because one we can measure more and the other one is very hard to measure. So we can have a more quantitative version of the idea too.
Okay, thank you.
Thank you. I will close the Zoom now. Thanks for your question. And we will,
Okay.